Hello. Today we're going to talk a little bit about using the ideal gas law. Before we can talk about using the ideal gas law, it is important for us to understand how we derive that law. Most of us are aware that there are numerous simple gas laws, such as Boyle's law, Charles' law, and Avogadro's law. Boyle's law relates pressure and volume at constant moles and temperature. Charles' law relates volume and Kelvin temperature at constant pressure and number of moles. And Avogadro's law relates volume and number of moles at constant pressure and temperature. If you combine these three laws, you arrive at the ideal gas law, PV equals nRT, where P is pressure, V is volume, N is the number of moles, T is the temperature in Kelvin, and R is the universal gas constant. If pressure is in atmospheres, volume is in liters, N is in moles, and temperature is in Kelvin, this gas constant R has the value of 0.0821 liter atmospheres per mole degree Kelvin. It turns out that if you remember the ideal gas law, you can derive from it the simpler gas laws we just saw. Perhaps this is best illustrated with an example. Suppose we are in a situation where temperature and volume change, but pressure and number of moles are constant. We can rearrange the ideal gas law then so that all of the constants, in this case N, R, and P, are on one side, and all of the variables, V and T in this case, are on another. If you rearrange the ideal gas law in this fashion, you get V over T equals N times R, all divided by P. N, R, and P are all constants. In other words, what we really have is V over T equals a constant. Well, if V over T equals a constant, then we can, for the same sample of gas, under different conditions, set things equal to each other. And we end up with V1 over T1 equals V2 over T2, where 1 and 2 are simply two different sets of conditions under which this gas sample exists. What is true about those two separate conditions? The amount of gas and the pressure the gas experiences in both cases must be constant. This is Charles' law, which we saw a moment ago when we began our discussion. In a similar fashion, one could use the ideal gas law to derive Boyle's law or Avogadro's law, which we also saw at the beginning of this video. This is just one of the handy uses of the ideal gas law. Let's look at a few others. Of course, we can use the ideal gas law to solve for any one of its variables, assuming we know the other four. For example, we could answer a question such as what is the pressure in atmospheres of a 0.350 mole sample of a gas at 22 degrees Celsius in a 5-liter container. Before we can solve this particular problem, we must convert our temperature to Kelvin. All gas laws use temperatures in Kelvin. 22 Celsius plus 273 Kelvin is 295 Kelvin. Plugging in what we know into the ideal gas law, in this case we do not have a pressure, that is what we're looking for. We plug in the volume of 5 liters, the number of moles is 0.350 moles, the gas constant 0.0821, and the temperature T 295 Kelvin. Solving then for P, we end up with a pressure of 1.70 atmospheres. We can also use the ideal gas law to calculate different things about a gas. For example, its density or its molar mass. Your textbook does an excellent job of laying out the steps involved in calculating the density of a gas using the ideal gas law. So instead of focusing on that topic, I chose to focus for a moment on calculating the molar mass of a gas. This is probably best illustrated by an example. Let's tackle this one. What is the molar mass of a 3.16 gram sample of a gas with a pressure of 0.750 atmospheres, a temperature of 45 Celsius, and a volume of 2.05 liters? We have a hint. The hint says solve for moles, which we'll do using the ideal gas law in just a moment, and molar mass is grams per mole, or grams divided by moles. So we will take the moles we get from the ideal gas law, we will divide the 3.16 grams of our sample by those moles to get the molar mass of the sample. Again, before we can carry out this calculation, we must convert the temperature to Kelvin. 45 Celsius is 318 Kelvin. Now we plug our numbers into the ideal gas law. This time we have a pressure of 0.750 atmospheres, a volume of 2.05 liters. We are looking for the number of moles N. Our gas constant is still 0.0821, and our temperature is 318 Kelvin. Solving for N, we get 0.0589 moles of this particular gas sample. Calculating the molar mass then, we take 3.16 grams of the sample divided by 0.0589 moles, and we get that the sample has a molar mass of 53.7 grams per mole. The final application of the ideal gas law that I want to discuss with you today very briefly is gas stoichiometry, meaning that we can use the ideal gas law to help us solve for information related to the gases in various chemical equations. Once we know that information, we can work with the chemical equation and its ratios of moles to find information about other reactants and products. This is perhaps best illustrated by a simple example. Limestone, which is calcium carbonate, reacts with hydrochloric acid HCl to produce calcium chloride, water, and carbon dioxide gas. You see the balanced equation for this reaction on the screen, where 1 calcium carbonate reacts with 2 hydrochloric acid to produce 1 calcium chloride, 1 carbon dioxide gas, and 1 mole of water vapor. The question: how many liters of carbon dioxide are produced at 752 millimeters of mercury and 24 degrees Celsius from a 25 gram sample of limestone, calcium, which is calcium carbonate? In this case, you will notice that our pressure is in millimeters of mercury, not in atmospheres. This problem is solved using a different value for R, the gas constant, because of the different unit on our pressure. In other words, because the pressure is not in atmospheres. You can, if you wish to use the same value for R, convert this pressure to atmospheres and use R equals 0.0821. Or you can remember this other value for R, which isn't given on your test like the other one is. I highly recommend that as you solve this problem, you do so first by converting the pressure to atmospheres. Additionally, of course, we have to begin by converting, we also have to convert our temperature to Kelvin. So 24 Celsius plus 273 Kelvin is 297 Kelvin. This problem requires that before we find the volume of CO2 in liters, that we use what we know about stoichiometry to calculate the moles of CO2. You notice in the ideal gas law, to begin with, we would be missing 2 variables otherwise. Both V and N would be absent from our equation. So we must use what we know about stoichiometry to find N before the ideal gas law becomes useful. 25.0 grams of calcium carbonate. Calcium carbonate has a molar mass of 100.1 grams per mole. So we're going to take 25 grams of calcium carbonate. We're going to divide by its molar mass to convert it to moles. The mole-to-mole ratio between calcium carbonate and CO2 is 1 to 1 from our balanced equation. So we have 1 mole of CO2 per 1 mole of calcium carbonate, which means that we have 0.250 moles of CO2. Plugging in that for N in the ideal gas law, converting our temperature to Kelvin, which is 297 Kelvin from 24 Celsius. We plug in P as 752 millimeters of mercury here. V is what we're looking for. N is 0.250 moles. T is 297 Kelvin. And because we are in millimeters of mercury, rather than convert it here, we are going to use the other value for R, which is 62.4 liters times millimeters of mercury per mole degree Kelvin. And we're going to solve for V and get 6.16 liters, which is the volume of CO2 that is produced when this reaction occurs. You should still get 6.16 liters if you first convert the 752 millimeters of mercury to atmospheres. You can do that by dividing by 760 and use 0.0821 as your value for R instead of the 62.4. I hope these applications of the ideal gas law help you to have a better understanding of gas laws and gas behavior.